Hi, I'm Sarah Watson, and this is my critical assignment. Chose to do solving linear equations with one variable. So the problem we're going to solve, let's see. Sorry, it's the first time I've done this. Okay, so our equation we're going to solve today is going to be x equals 15.5 multiplied by 150 divided by 100 squared multiplied by 200 divided by 100. So the first thing we're going to do is rewrite the fraction. So we're going to rewrite it so everything is over 1. So you take and you put 15.5 times 150 divided by 100 squared over 1, and then multiplied by 200 over 1. Then you're going to go ahead and find the greatest common factor and cancel that out, which in this case is going to be 100, and rewrite, and remember to move the decimal. Again, this is all in my own words, and it's not always correct, but in terms of the verbiage, this problem should come out fine. Anyways, so then you rewrite, and you remember to move that decimal. So you have x equals 0.155 multiplied by 150 divided by 100 squared over 1, and again, multiply that by 200 over 1. So the next thing you do is you go through our sequence, which means parentheses come first. So x is multiplied then. Okay, so what you're going to do here to get this 3.2 from the 150, you'll see, I lost my little guy. You'll see all of a sudden here we have 3 over 2. Where did that come from? That came from right here. What you're going to do is you're going to go through and you're going to factor this out. So you have the greatest common factor with 150 and 100 is 50, and you just keep factoring it until you get down as low as you possibly can go, and then you'll end up with 3 over 2. So now we have this as our new equation. So you're going to go through now, and now we can start multiplying and actually doing something with these numbers as opposed to just minimizing them and minimizing them. So here now we're going to multiply our 0.155, times the 3 over 2 squared, and that's going to come out to 0.34875. Rewrite it and combine, because again these are fractions, and so now you have these as written as fractions, right? So you're going to take this and put the whole thing over 1. So you're shifting it over. And once you do this multiplication, you get 69.75, which in this case is your answer. Where did this come from, and why is this even useful? This is useful to a lot of people every day. This particular equation is used in firefighting. So this example that I used is designed for firefighters, and we're going to go ahead and rewrite this equation. Here's our formula right here. It doesn't look the same as the last one. You see, doesn't look the same. Well, it doesn't look the same because we didn't start the same. But this is what firefighters use, specifically engineers, every single day to make sure that there's enough water coming out the end of the hose for the firefighters on the ground that are spraying the water onto the fire, into the house, or whatever it is they're trying to save. And basically the way it works is your X becomes friction loss. Okay, that's what they're trying to find. They need to know how much water is actually coming out, how much water are they losing because they've connected 2 pieces of hose together. So what happens is when you take 2 pieces of hose and you connect them together, right in the middle of the joint, let me see if I can, right here at this joint where they're connected together, they actually lose water pressure. Doesn't sound like a big deal when you're not the one fighting the fire, but when you learn a little bit more about fire, you learn that on the other end of the hose, losing pressure means losing water. That means less water that's getting onto the fire, more water that's evaporating into the air because of this friction loss. So hose comes in 50-foot lengths. That's why I chose to do this problem here, which is the 200, just to keep it easy. Makes it easy. 200 feet. Okay, so here's what we have going on here. Oops. F becomes friction loss, and that was your X. This is where X was. Where did my pointer go now? Here we go. So this used to be X. C, you see, is a friction loss coefficient. The friction loss coefficient was our 15.5. Okay, and you get that coefficient over here, you'll see different hose diameters. Well, in the fire service, basically what happens is for a standardized attack hose, they use 1 3/4 inch hose. That's the size of the hose. And for that, they've already figured out that the coefficient is going to be 15.5. Now, this table is not, general knowledge, obviously. It's something very specific to fire service, but it's something very important. Then you have Q. You have Q right here. And Q was, Q was 150. So 150 is the standard rate of water coming out of a fire truck at any point in time. So when they hook a hose up, typically speaking, they will run 150 gallons per minute out of that engine into the fire. With the 50-foot hose, that's not a problem. But when you start adding lengths of hose, again, they come in 50-foot lengths, so you need a little bit more hose, a little bit more hose, a little bit more hose. Now you're looking at running 200 feet of hose, which again, that's where we get this from, hose length, that's L. For us, that was 200. You're looking at having 4 pieces of hose. With each one of those couplings or each one of those little joints, you lose that water pressure. So how much pressure is getting to the guys on the ground from the truck? When you're talking about 200 feet, you're not standing next to each other. So it's not easy for the engineer to see what's happening at the fire. That's where this equation comes into play. With our equation, what basically happens is they figure out exactly how much water is getting there. So the answer to this equation was 69.75. That's actually an accepted rate of water loss. So that's the percentage that is being lost at the nozzle. So when the engineer starts out, he's doing great. He's got 100% water flowing out of the truck. By the time it gets to the guys on the ground, 200 feet later, you're looking at a 69.7% loss, which is actually an acceptable rate in the fire service for an attack rate. Once they get to a 75% loss, the engineer needs to make some adjustments, up that water pressure so he's got more gallons per minute flowing through. If he puts too much water pressure through that hose, the hose can split. Your hose splits, you have no hose, your fire doesn't get put out on time. So this particular equation is extremely important and has kind of a superpower of its own in figuring out how to save lives and property.